So number 9 then from the 2015 Advanced Higher Maths, we've got this little identity to prove involving combinations for 4 marks. Now there's actually 2 ways to do this. You've actually seen this problem before where you've expressed it as factorials and then just resolved it. But you could also look at that and think that's just like one of those proof by induction problems. So we'll have to do it both ways. Now that would actually be quite quick to write out if you're allowed just to express that the way it was originally developed, as in if you had 5, you could put C2 or just 5, 2. You would just say how many ways are there of selecting 2 objects from 5? Well, there's 5 ways for the first, there's 4 ways for the second, but that includes either of them coming first, so divide it out by the number of permutations, 2 times 1, which simply means for this you would just have to write out the first 3 terms of this descending, and for this you would just have to write out the first 3 terms of that descending. In the marking scheme that takes about 3 lines to get there, as if they want you to use the resulting formula, which is a bit of a pest because understanding this means understanding that. So they actually want to use that general case where, admittedly it's not so easy to write this out. If there were a selection of R objects, it would be over R factorial. So you'd have to write out the first R terms of n factorial, which is a bit of a pest. So what you do is you write it all out and then put the balance of them, that's n minus R, underneath to cancel those out. So it looks as if they want you to put the whole show down here. So just have to do that, I suppose. But better just to jump straight in. Still, what does it stand for? It actually stands for, maybe I shouldn't have put that line quite so long. It stands for n plus 2 factorial over 3 factorial. I only wanted the first 3 of those, so I'll have to say, well, that'll be n plus 2 minus the 3 factorial. Oops. Similarly for this one. And of course what I'm doing is an identity. I should be saying this is the left hand side. Right, and that's going to be n factorial over, yes, 3 factorial. And I only want the first 3 of them, so take away the rest, n minus 3 factorial. That appears to be the first mark. Then, you know what this is going to come to. Then, multiplying this out, what have we got? We know what that factorial means. It means you've got n plus 2 times n plus 1, but this part here is n minus 1. So, n, and now we're down to n minus 1. So I don't need to write the rest because that will be the same as this part, so factorial for the rest of them. Over, and of course that part there was n minus 1 factorial. And 3 factorial, it's only 6, we'll pop it back in, that's 6. Similarly for this, n factorial means n times n minus 1, that's n minus 3, times n minus 2, that's n minus 3, times n minus 3. Now we're there, so the rest of the factorial can just be put as factorial. And that's all over. N minus 3 factorial times 6. They seem to want you to write all of that out. Still not arrived at the obvious, which is now when I cancel this out, I get, which you knew all along. What does that really mean? It means n plus 2 times n plus 1 times n all over 6, or rather 3 times 2 times 1. Minus, and what does this mean? N times n minus 1 times n minus 2, the first 3 terms, over 3 times 2 times 1, which is 6. Those 2 bits cancelling out. Don't see what's wrong with going straight in with this, because that is a definition you know for a numerical value. Still, there you go, can't complain. So that means you've got, now take out some common factors. They both have got n, they both got over 6, and that's all they've got, so I've got n upon 6 times, that's just a wee quadratic there. Could even multiply it out straight onto the spot. So I've got n squared plus 3n plus 2 minus, and that's just a wee quadratic there, just multiply it out into the spot. I've got n squared minus 3n plus 2. Oh, that's quite good, because subtracting them, they subtract, and I've got 6n. So I've got n upon 6 times 6n, which equals n squared as required, which equals right hand side. Now I know that's the 4th mark obviously, but I don't know where the 3rd mark comes. Correctly expressing with a common denominator. So that must be this line then. That's 3 marks to get to the obvious expansion of that. Anyway, that's one way. So the other way, looking at that as an indirect proof, a proof by induction, it's going to be a bit lengthier because you know all the statements you're going to have to go through. Well, you'd have to try this. First of all, you say, well, first of all, we'll test it for the initial. The initial one is n equals 3. So we're going to test it at n equals 3. Does it work? So that means you've got 5, 3, I should have said left-hand side, minus 3, 3. And of course, straight away to evaluate that, I know you could press the buttons in your calculator, but that means, well, I'll put it, 5 times 4 times 3 over 3 times 2 times 1. They all cancel out to 10, so that's 10. And 3, 3 would be 3 times 2 times 1 over 3 times 2 times 1, so that's obviously 1. So that comes to 9. The right-hand side is 3 squared. That also comes to 9, so you can say this then for the first mark. So it's true for n equals 3. I omitted to state left-hand side equals right-hand side. Still not the first mark. The first mark according to the marking scheme is the base case. That's this one, the first one. And the assumptive hypothesis. All right, we'll have to put that down, so we'll have to say that. So, assume true for n equals some arbitrary number further along k, which means you'd make the statement k plus 2, 3 minus k 3 should equal k squared. There's your inductive hypothesis. Now you get the first mark. Right, another thing is I'll need a lot of room. Another thing you have to do is using an inductive proof, which is an indirect proof, you have to watch that at the next step when you say this. So it's going to consider the next case. Remember, the inductive proof is a stepping stone one. If it's true for one, it's true for the next. Consider n equals k plus 1, so in which case you put that into this expression so that you've got this. You've got k plus 1 plus 2 minus k3. You have to consider what that might come to. Oops, k plus 1, 3. Don't just treat that the same as the previous case and expand it in terms of its factorials and resolve it down to the result without even considering this, because that would be a direct proof and that wouldn't be a proof by induction. So that means you won't be using that root of the factorials. You'll have to find some other pattern for this. I'll just write that again neatly. So that's k plus 3, 3 minus k plus 1, 3. So you won't be using that factorial pattern, you'll be using that other pattern, the one you know from the Pascal's triangle, the way it builds up. Down the way, you've got the n. Along the way, you've got the ones you're selecting from it. And the pattern is to get the ones below. You add these two to get this one down here. You need to remember that little identity. That identity would be nr plus the next one along the same row, nr plus 1, gives the one below. So that would be, the row below would be n plus 1, but the same one as this, r plus 1. You'll need to use this to try and sort this thing out. But at some point, you're going to have to introduce your inductive hypothesis to resolve some of this. So from this, I need to recreate this somewhere. Well, the way you could recreate that would be just to take a step back, taking that as the result. What would that have been produced from? So I could have, instead of the k plus 3, stepping back up the first two, that would have been from the sum of the row above. That would have been k plus 2. And if that was at 3, it would have been 3 and 2. So that's a 2 and that's a 3. So that's one of those parts here. I need this k. We'll do the same with this one. Step that one back up. In fact, that looks very much the same as that. Step that one back up into its original pair. Remember, it would be a plus, so it'll be a minus here, because it'll be minus the sum of those two. So minus this one as well. So that says that would have stepped up to just k. So the two rows here would say k. And if that's a 3, then that's a 3 and that's a 2. That's a 3 and that's a 2. Quite a bit of jiggery-pokery doing it this way. Now I can recreate that here. So I've got my k plus 2, 3, and my take away k3, that's those two parts, but I've still got my k plus 2 and minus my k2. Whereupon I'll now call in my trump card. I'll call in the inductive hypothesis to change this into simply k squared. And now, ironically, I've got to think, what am I going to do with this thing here? Which isn't much different from what you had to begin with. The only difference here is it's got a 2 instead of a 3. And lo and behold, what will I do with that? I'll just write out what they actually mean. But here they seem to be quite happy to say, oh, what does that mean? Oh, but it's only the first two terms. So that'll be k plus 1. No, it's not. K plus 2, k plus 1 over 2 times 1. And that's minus, by the way, k times k minus 1 over 2 times 1. They're quite happy with that. So why not just have done that in the first part and saved all that palaver? But anyway, notice that little direct bit of manipulation hasn't affected the fact that you're still doing a proof by induction though. Of course, while we're still doing this, the rest of them now at question 11. Right, where was I? So we've got k squared plus, there's a common factor there of a half, so it's a half of, and now just expand that lot. So we've got a k squared plus a 3k plus a 2 minus a k squared minus a k. Run out of room, so I'll have to pop it up here. Right, so what have we got now? We've got k squared plus a half of, and that's, the k squares disappear and you've got 3k, but take away negative is 4k. And that's plus 2. So you've got k squared plus 2k plus 1, which is k plus 1 squared, which is the required result. Required result for n equals k plus 1. So what have you just proved? You've proved this then. You've proved that true for n equals k meant it was true for n equals k plus 1. And since it's true for n equals 1, that means by that stepping stone principle, if it's true for one, it's true for the next. That means that, or you could just say by induction, it's true for all. Ooh, true for n equals 3. It means it's true for all n greater than or equal to 3. There we go then. If you fancied a wee proof by induction, result. Of course, in my haste I missed out where the marks went, but it doesn't really matter because it was just a fabrication of marks anyway. Where you spread 4 marks amongst that lot. Obviously, the final result, that's the 4th mark, and the initial bit, the base statement and the inductive hypothesis, that was a mark, but the other two, but basically, I suppose, just for knowing that little identity. Remember that one? For combinations, and also for knowing how to expand one of these. But of course, that misses out all the algebra you had to do in between. Never mind, it's out the way now.